Good morning, students. Myself, Dr. S. Devikala, Associate Professor in the Department of Chemistry, SRM Institute of Science and Technology. In today's class, let us see some of the organic reactions which are well known, like addition reaction, elimination reactions, free radical reactions, oxidation, reduction, and so on. Let us see one by one. So, if I say the reactions with respect to substitution reaction, substitution is nothing but generally replacement. One group is being replaced by another, that is called as substitution reaction. Under substitution, you have different types: nucleophilic substitution, electrophilic substitution, radical substitution. So under electrophilic substitution, you can see electrophilic aliphatic substitution as well as aromatic substitution. In nucleophilic substitution, you have SN1, SN2. In addition to that, nucleophilic adiabatic substitution, aromatic substitution, and acyl substitution. Let us see one by one. Generally, what are nucleophiles? Nucleophiles means they are electron rich. Since they are rich, they are ready to donate electrons to other atoms. So who will be accepting electrophile? So nucleophiles are nothing but electron rich species, whereas electrophile means electron loving or electron deficient. It needs electron so that it can easily accept electron. So a nucleophile is an electron-rich species that will react with an electron-deficient species. The electron-deficient species are nothing but your electrophiles. A substitution implies that one group replaces another. That's what I told you now. So replacement only. So nucleophilic substitution reactions occur when an electron-rich species, that is the nucleophile, reacts at an electrophilic saturated carbon atom attached to an electronegative group. Then the leaving group, the electronegative group, it leaves the carbon center that can be replaced as shown by the general scheme. So this is the carbon. Lg is nothing but leaving group, any halide group usually. Then Nu minus is nothing but nucleophile. Nucleophile, as I told you, it is electron rich. So while writing itself, we have to write it as Nu minus only. So when the nucleophile is going to attack this carbon, it is getting attached to the carbon, whereas the leaving group, name itself leaving group, so the halide will go out. The electrophilic carbon can be recognized by looking for the polar sigma bond due to the presence of an electronegative substituent, especially CCl, CBr, Ci, and CO. Nucleophilic substitution reactions are an important class of reaction that allow the interconversion of functional groups. Of particular importance are the reactions of alkyl halides, that is Rx, here R stands for alkyl, X stands for alkyl, and alcohols, ROH. For alcohols, the range of substitution reactions possible can be increased by utilizing the tosylates, that is OTS, an alternative method of converting OH to a better leaving group. Let us see the SN1 mechanism with an example. Here, S stands for substitution, N stands for nucleophilic, 1 stands for unimolecular reaction. So it is given by the rate expression. So here, the rate determining step of the mechanism, it depends on the decomposition of single molecular species alone. It is unimolecular reaction, so it involves two steps. Step 1 is loss of leaving group. Step 2, the attack of nucleophile on the electrophilic carbocation to form a new sigma bond. S bond is nothing but new sigma bond. So first step, the removal or the loss of leaving group. Halide ion will go out, that is Lg minus. And then the second step, nucleophilic attack. So here the carbon is represented by plus sign. So this carbon with the plus sign, it is called as carbocation. That too, it is electrophilic. Why it is electrophilic? Plus charge is carried by carbon. That means it needs electron. So the step-by-step mechanism of reaction of alcohols with HBr is given over here. So step 1, protonation of the alcoholic oxygen to make a better leaving group. This step is very fast and reversible. The lone pairs on the oxygen make it a Lewis base. Then step 2, cleavage of the CO bond, which allows the loss of leaving group, a neutral water molecule, to give a carbocation intermediate. This is the rate determining step. So here the bond breaking is endothermic. And then step 3, attack of nucleophilic bromide ion on the electrophile carbocation. It creates the alkyl bromide. Let us move on to SN2 mechanism. Once again, S substitution, N nucleophile, 2 bimolecular reaction, that is given by the rate expression. So here the rate determining step, it involves interaction between two species, the nucleophile and the organic substrate. So it is a single step process. The attack as well as the leaving group, it takes place simultaneously. So it is a single step process. So next one, electrophilic substitution, that too aromatic electrophilic substitution. So here, what is this? It is nothing but your benzene. Electrophile is going to attack. So addition of electrophile making the Ce bond, and then we'll get several resonating structures, resonance, and then finally proton transfer, so that the group is attached here, replaced here. So benzene and bromination with Br2 and FeBr3, it gives Br. So the electrophilic substitution mechanism is given in the small box. Formation of electrophile, how the electrophile is formed. First the electrophiles are generated, and then the electrophilic attack. Finally the product is formed. The product formed is bromobenzene. The next one, free radical. So free radicals are highly reactive, highly unstable. So you can find ethane, methyl anion, methyl cation, methyl radical. So any free radical substitution means it involves generation of free radical followed by chain initiation, propagation and termination. Always it involves 3 steps. So let us consider the chlorination of methane. So here the homolytic breaking of covalent bond occurs. So Cl2 is cleaved homolytically. As a result, you will get Cl dot, that is chlorine radical. So overall reaction required is methane and chlorination. You will get methyl chloride, methylene chloride, carbon tetrachloride via chloroform. So the condition, ultraviolet light, that is H nu, over the arrow mark you will be writing it as H nu, that is nothing but UV light, excess methane to reduce further substitution. So any free radical substitution reaction means it involves chain initiation, propagation, that is continuation, finally the termination step. This is what I told you, homolytic fission, Cl2, H nu. So chlorine radicals, once the chlorine radicals are generated, they are highly reactive. So it can attack methane. As a result, methyl radical plus HCl, the chain is said to be continued or propagated. Finally, the chain termination. In order to terminate any chain reaction, two free radicals combine to give the required product or desired product. Let us move on to elimination reactions and oxidation reaction. Elimination reactions are nothing but these are reverse of addition reaction. So we have to eliminate the groups or functional groups attached to adjacent carbon atom. As a result, the resultant product, it will be an alkene. So elimination reactions are those in which two atoms or groups of atoms get eliminated to form a substrate molecule, to form generally a unsaturated compound. That's why I told you alkene. Molecular weight of product is less than the starting material or substrate. Like SN1 and SN2, in elimination also we have E1 and E2. So here E1, E stands for elimination, 1 stands for unimolecular. Again, one unimolecular, any unimolecular reaction means it involves 2 steps. So here tertiary butyl chloride is stirred in a mixture of ethanol and water. A mixture of SN1 products, that is tertiary butyl alcohol and tertiary butyl ethyl ether, whereas E1 product 2-methyl propene. You can find this is your 2-methyl propene. Elimination reaction, bimolecular. Again, E stands for elimination, 2 stands for bimolecular. It is a single step process. So tertiary butyl bromide with concentrated solution of sodium hydroxide. The product formed is 2-methyl-propene. This is the structure of 2-methyl-propene. Oxidation. Let us move on to oxidation reaction. So methane can be oxidized to methanol, further aldehydes to acids. Finally, several oxidizing agents are used. The well known is KMnO4. So aldehydes are readily oxidized to acids or carboxylic acid with help of KMnO4. So KMnO4, that is the well known oxidizing agent, whereas itself it undergoes oxidation. Everybody knows that. Then alcohols to aldehydes to acids. Similarly, oxidation in aromatic molecules also. Like KMnO4, K2Cr2O7, K2Cr2O7, that is potassium dichromate is also used. Let us move on to reduction reactions. Reduction, it is nothing but decrease in oxidation state or addition of hydrogen related to the carbon atom, that is ketones to alcohol, C double bond O to CHOH. So the source of reduction, some of the reducing agents are sodium borohydride, lithium aluminum hydride, hydride nucleophile, so ketone to secondary alcohol. Suppose if these two R is replaced by CH3, means the formula will be CH3 C double bond O CH3. So the product formed is CH3 CHOH CH3. That is the secondary alcohol. Next, let us see what are cyclization reaction. Under cyclization reaction, we will be discussing about Dickmann condensation. Under ring opening reaction, conversion of cyclic compound into non-cyclic compound. That is how certain reagents are added to cyclopropane. So in case of cyclization, the formation of ring in a chemical compound. Reactant side, you have only a cyclic compound, whereas we will be ending with the cyclic compound. So in this, we will be discussing about the Dickmann condensation or Dickmann cyclization. It is nothing but conversion of diesters into beta ketoester. That is the short explanation. So here you have diesters C double bond O CH3, C double bond O CH3. So the reactant is diester, whereas the product formed is beta keto ester. A cyclic compound we are converting into cyclic compound using the reagents mentioned over here. The next one, ring opening reactions. So here we'll be discussing about the ring opening reactions of cyclopropane. So cyclopropane has large ring strain due to a mixture of angle strain and torsional strain. So this is the structure CH2, CH2, CH2. Here the bond is said to be broken between 1 and 3. Let us see the products. So formation of cyclopropane ring with the sodium, how cyclopropane is produced. Okay, from di 1,3 dihalides. So cyclopropane on chlorination, it forms 1,3 dichloropropane. The reaction takes place in dark as well as in presence of light. And then bromination, that's what I told you, the bond is said to be cleaved here, broken here, so that you will get 1,3 dibromopropane. Addition of hydrogen iodide to the same cyclopropane, again the bond is said to be cleaved here. So the product formed is, you will get CH3, CH2, CH2I. And then addition of sulfuric acid, again H will be added to this carbon. So CH3, CH2, CH2, HSO. HSO4. So it is propyl hydrogen sulfate. The product formed is propyl hydrogen sulfate. Then reduction of cyclopropane to cycloalkane. So when a molecule of H2 is added, bond is broken here, no? So CH3, CH2, CH3. Normal propane is the product. Let us see some of the commonly used drug molecules. Let us see what are drug molecules with examples. So what is a drug? Drugs are natural and synthetic. It may be organic or inorganic, or in some case it may be organometallic compounds that is used to diagnose, cure, treat, or prevent diseases. These are also called medication or therapeutics. Some of the commonly used drugs are ampicillin, you see the structure here, paracetamol, penicillin, aspirin, and amoxicillin. Here paracetamol is used as antipyretic, whereas aspirin analgesic. So the different drugs, drug discovery, pharmacology, quality assurance and quality control, drug metabolism, organic chemistry, pharmacodynamics, pharmacokinetics, just for your reference. So paracetamol, as I told you, antipyretic, whereas aspirin used as analgesic. So in order to prepare paracetamol, the starting material is para-aminophenol. So in this slide, you can see how para-aminophenol is prepared from phenol using dilute sulfuric acid and sodium nitrate. The next one, synthesis of aspirin and its uses. Aspirin, as I told you, it is used as analgesic. So the starting material is phenol. Phenol reacts with sodium hydroxide. It forms sodium phenoxide. Sodium phenoxide with the CO2 treatment, it forms sodium salicylate. Sodium salicylate on hydrolysis, you will get salicylic acid. Then salicylic acid, when it is treated with acetic anhydride, the final product formed is aspirin. That is acetyl salicylic acid. It is used as analgesic. Okay, so in today's class, we have seen some of the very important organic reactions, oxidation reactions, reduction reaction, elimination, substitution, and the two important drugs preparation also we have seen. I hope you have understood today's class. Thank you.